continue our afternoon with Emanuela Giacomelli, LMU Munich, who will be describing the response of a superconductor with corners to an external magnetic field with a certain intensity regime, a talk titled Corner Contribution to Surface Superconductivity. So, Emanuela, welcome.
So, hi everybody, and thanks a lot to Vafa, Iman, and Michele for the invitation. Before starting, let me say that it's really a pleasure for me to give this talk in this conference because there are many of the authors of the papers I was reading during my PhD. So I think that this is the right community to talk about this topic, also in the perspective maybe of solving some open problems and improving our results. So here you find the references for the 3 papers which contains all the results I'm going to talk about today. And let me start with introducing the Ginzburg-Landau functional and telling you which is the main problem we want to look at. So we want to our big goal is to study the response of an infinite wire with cross-section omega to a uniform applied magnetic field, which we suppose to be perpendicular to the section omega, and of constant intensity, which I denoted by Hx. And if you want, the equilibrium state of this system is given by the minimizer, so the minimum of this energy functional, which is called Ginzburg-Landau functional, and this is a functional which depends on a parameter k, about which I will comment later, and about 2 quantities, which are psi, an order parameter, and a vector potential. So in particular, this psi here is such that if you look at the modulus square, this just tells you which is the density of the superconducting Cooper pairs, which are just pairs of electrons, which are responsible for the superconducting properties. And instead, if you look at the phase of psi, then this phase contains information about the current which flows in the superconductor, which is given by this quantity here. And instead, by A, actually, we measure A with respect to the intensity Hx here. So Hxa is nothing else than the induced magnetic vector potential. And finally, I told you that this is a function of which depends also on a parameter. This parameter is called is kappa, and this is called Ginzburg-Landau parameter. And if you want, this is a quantity which is given by proportional to the inverse of the penetration depth. We want to look at particular kind of superconductor, which are called type 2 superconductor. And this means that, so I didn't tell you, but I think that you know that this parameter is typical of the material. And the material we want to look at are such that K is very, very big. And that's why we study the minimum of this energy functional in the asymptotics in which K goes to infinity. I think that I told you everything about this slide. So let me go on. Okay, maybe I want to underline that the dependence on Hx in the functional it's here, and then you see that depending on this value here, you can see different, you can have different behaviors of your minimizing pair psi A. And in particular, what I just want to underline here is that if the intensity of the external field is really, really small, we can say that this is almost 0, then the only minimizer of the Ginzburg-Landau energy functional is given by a pair, psi A, where in particular psi is such that the modulus of psi is identically equal to 1. And this means that the density of the Cooper pairs is equal to 1. So all the electrons are paired. And if you want, I didn't write here, but the induced vector potential has to be thought as equal to 0. This means that our sample is in the so-called superconducting states, in Meissner states, in which there are all the superconducting properties. On the opposite, what happens if you increase enough the intensity of the external field is that So meaning that you apply a usual magnetic field, then the unique minimizer is given by what is called normal state, in which instead you see that the modulus of psi is equal to 0. So this means that there are no Cooper pairs. And actually here I didn't write again, but A is such that the curl of A equals the external magnetic field. I think that it's clear that since these are two opposite situations, then would be really interesting to know what happens in all the intermediate case, meaning in the case in which the intensity of the field is not so small but not so huge. In this case, what we say is that we work with mixed states in which the modulus of psi is in general positive but less or equal than 1. And now, in the next slide, what I'm going to do is to tell you more or less which is the story about what happens between these two states, and then I will focus on the regime we studied. So first of all, as I was saying before, here you see if the intensity of the field is small enough, then what we have is that we are in the superconducting state in which the modulus of psi, I already told you, it's exactly equal to 1. In this case, if you want to study, so I denoted by this quantity here, just the minimum of the Ginzburg-Landau functional, and if you want to study this minimum here in the limit as k goes to infinity, what you can write is that at least reading order, this minimum is given by this quantity here. So this is nothing else than the Ginzburg-Landau functional, which is evaluated over psi. So this one means that modulus of psi is equal to 1, and you have to minimize this functional here with respect to NA. And actually, if you do calculations, you see that this A is exactly the one which such that curl of A is equal to the external field. So this is what happens if you are in the Meissner state. As soon as you increase a little bit the intensity of the field, in particular, if you are in this situation here, then what happens is that if you look at, so now psi GL is nothing else than the minimizing psi. So what happens is that psi GL contains at least one vortex. And in this context, having a vortex means that you lose the superconducting properties exactly at the vortex. So here and in any other slides, I try to write here people who work on these things. And let me just say that as soon as this is satisfied, then you know that you can prove that psi GL has at least one vortex, but then the number of vortices increases as soon as you increase the intensity of the field. And at the end, what happens is that this vortices covers all the interior part of your sample in such a way that if you then reach this second critical field given by a constant B times kappa square, then superconductivity survives just close to the boundary of your sample omega. And in fact, if you look at the infimum of the Ginzburg-Landau functional, then this is just described by this quantity here, which I will comment also later. But here I just want to underline that you can, since superconductivity survives just close to the boundary, you can describe this infimum here with respect to quantities which are living close to the boundary, actually. And let me just say that this is what happened just in the case of smooth domain. And actually what we want to discuss today is what happened in the case of domains in which there are a finite number of corners along the boundary. So just to have in mind, this is the regime I want to focus on. But before doing that, I would like to tell you the full story, meaning that if then you increase a little bit more the intensity of the field and you reach a quantity which so far I just called C3, which is a quantity which of course depends on kappa, then the only Ginzburg-Landau minimizer is given by this pair here. And what you should have in mind is that in this case, as soon as you are above this critical field, then your sample, your metal has no any superconducting properties. So why here I just wrote AC3, because the value of AC3 strongly depends on the domain you are working with. In particular, if your domain omega is a domain which is smooth, then it is proved that this critical value is given by this quantity here, which then in fact I called AC3 smooth. I don't want to comment more a lot about this, but let me just say that this θ0 is nothing else than a spectral parameters, which is strictly related to the spectral parameters which are denoted by lambda, which appears at the leading order of the third critical field in the case in which there are corners along the boundary of your domain omega. So you see that here you start to see the difference in adding corners along the boundary of omega, and in particular, what could be interesting is to compare the two values of this third critical field. So there are many. So there are conjectures about. So maybe I want to write something. So this lambda is nothing else than determined by. So is the minimum of a quantity which I called mu alpha, which is just equal to the infimum of the spectrum of an operator which is given by minus I gradient plus 1/2 R perpendicular square. So this is nothing else than the magnetic Laplacian with this vector field. And about this mu alpha here, there are several conjectures. In particular, it is so this alpha is nothing else. I'm just taking the infimum over an infinite angular sector which opening angle alpha. And if you want, since now I wrote this operator here, this θ0 is nothing else than the infimum of the same operator just in the alpha plane. Anyway, what I wanted to say is that there are several conjectures about how this mu alpha depends on alpha, and in particular, what is rigorously proved so far is that as soon as alpha is an angle which is less than pi/2, then this value here is strictly less than θ0. And because of that, what we can say is that if in your domain there is at least an angle which has an opening angle alpha smaller than pi/2, then the third critical field in presence of corners is bigger or equal, actually much bigger than the third critical field in the smooth case. This is not the, so you see that in presence of corners, you can see what happens is that you could have some more phenomena. And in fact, what happened is that you can also try to discuss the concentration of superconductivity close to the corner. And in this case, if you take it into account then an external field, which is between, whose intensity is between the third critical field in the smooth case and the third critical field in presence of corners, then what you can say is that if you look at, again, the minimum of the Ginzburg-Down functional, then this is well approximated in the limit as k goes to infinity by the sum of some function, by the infimum of the sum of some energy functionals, which are denoted by this quantity here, which are just living close to the corners. And moreover, and this is really the last thing I know it's proved about all of this concentration of superconductivity, but our result, what we know is that if you have many corners along the boundary, then what you can do, and this is, don't read here, what you can do is to label the vertices as J in such a way that you can introduce several critical field HC3J always between this interval here, which describes how superconductivity concentrates close to the J corner. Okay, so I try to tell you whatever is known so far or was known until I started my PhD about concentration of superconductivity in smooth domains and in domains with corners. And then what we did was to try to look at what happens in the surface superconductivity regime in the case in which you have corners along the boundary. And then you see that I hope that I convinced you that what we can try to prove is to introduce a new critical field, which so far we just call H corner, such that the critical field is between kappa square, which I remember you is nothing else than HC2, and it's bounded by the third critical field of smooth domain, and try to see if in presence of corners there is still concentration of superconductivity along a boundary layer. So this is the problem we want to look at. And before doing that, let me just show you this picture, which I borrowed from Vafa, because she together with Ayman and Michael studied what happens in the case in which you have magnetic fields which are piecewise constant. In particular, you see that this is the situation they have, and the jump of the field happens along this curve here, which they're supposed to be smooth. And what they proved is that actually, depending on some critical fields, then you can prove that you have superconductivity survives just first close to the boundary, and then close to the points in which the magnetic barrier meet the boundary, and then you have that you lose completely superconductivity. And there is this picture shows you a nice analogy about what happens with corners, because as I told you, in presence of corners, what we want to do is to show that there is superconductivity in this boundary layer, and then what is already known is that before disappearing, superconductivity concentrates close to the corners. So I think that now I'm ready to show you our main result. But before doing that, let me just show this picture. What I want to underline here is that in our domain, we suppose that there are just a finite number of corners. And moreover, okay, and as you can imagine, since there are corners, then the unit inward normal is well defined everywhere, but at the singularity. And we are not going to consider such kind of situations. So before showing the main result, I forgot about this slide. What I want to do is to do just nothing else than a change of units, because it's just more convenient to use with these units in our regime. So first of all, we want to focus in this regime in which the intensity of the field is between HC2 and the H corner. And so far, the intensity of the field was given by, so in this case, HC2 is given by B kappa square. And let me just define epsilon, which is defined like that. So since we want to look the limit as k goes to infinity, epsilon is going to be very, very small in our setting. And so what we're going to do is to then rewrite the Ginsu-Landau function in these units. And this is nothing else than the minimization domain we want to work with. And now there are just some notation. So by EGL epsilon, I denote the minimum of this functional here in this domain here. And by psi GL, AGL, I just denote any minimizing pair. And let me recall what I just told you before. So if omega is smooth, then you know that there is surface superconductivity regime in the case in which Hx is between AC2 and AC3s, which means that B, the parameter we have here now, is between 1 and theta 0 to the -1. Our question is what happens in presence of corners, and what we want to prove is that actually that for the same values of B, there is a concentration of superconductivity just close to the boundary of our domain. So this is finally our main result, and here I just brought the two papers you should look at if you want to see more details. So what we do is the following. We suppose that there are finite number of corners along the boundary of omega, and then what we proved is that for any fixed B in this interval here, as soon as epsilon goes to 0, we can characterize the minimum of the Ginsu-Landau functional by this quantity here. So the leading order is just a quantity which depends on the length of the domain here times a quantity which I'm going to introduce soon. And then you see that if you want to go beyond, what happens is that you can describe the correction just by the integral of the curvature of the boundary. And here I forgot to write an S because of course this is just true in the smooth part of our boundary. And then you see that you have a contribution coming from the corners, which is described by this sum here. So before comments a little bit on the corner contribution, let me say that instead, if you don't have corners, so you are working with smooth domain, then this is the asymptotic you can prove as soon as epsilon goes to 0. And this was proved by Michele Correggi and Nicolas Ruggieri. You see that you have exactly the same asymptotics as the one you have here, but here you have another contribution, which is the one coming from the corners. So since I have a pen, let me write that here there should be an S because this is just true in the smooth part of the domain. So about the contribution coming from the corner, so this green contribution, so sorry, I forgot to say that by this capital sigma, I just denote the set of all corners. So for each corner, I have this kind of contribution, and this contribution is defined in this way here. So let me start to tell you why we have this limit here. So in our analysis, what we do is to work with rescaled coordinates, and then I want to send these two quantities to infinity because I want to zoom in the region close to the corner. By gamma j here, I denote the region close to the corner. I show you soon which kind of region we need to choose. And what I want to underline now is that if you want to look at the corner contribution, then you have to, so we define this contribution in this way, in which this minimization here is just with respect to psi. So we fix the vector potential equal to F. And if you want, the psi you should look at in this minimization problem is a psi which is taken inside a domain where you put some Dirichlet boundary condition in this region gamma j. I talk a bit about that also later. And before going on, let me say that if you look at the definition of E corner J, then here you see that there is a minus this big quantity here, and this is just describing the leading order which we already took into account here. I think that this is gonna be more clear as soon as I show you how this gamma J is chosen. But before doing that, let me tell you, because I think that it's instructing how we can work if we just want to recover the first leading order, which is given by the length of the boundary over epsilon times this quantity here. So first of all, since in our regime, superconductivity is surviving just close to the boundary, what we can do is to use some Gauss-Bonnet estimates to say that the infimum of the energy, it's really, really small, but in a boundary layer, so close to the boundary. Then, if you want just to recover this leading order, what you can do is to discard the energy contribution coming from regions close to the corner and just work in the other part of the domain in which the boundary is smooth. If you do that, then what you can do is actually to reproduce the same analysis which was done by Michele and Nicolas for smooth domain. And then the idea you should have in mind in this case here is that the main part is to write down psi GL, so the minimizing psi, like in this way here. So you can write this like a product of a function f0, which is just a function of t, which is the rescale distance from the boundary, times a phase here, which depends on alpha, which is a real parameter, and s, which is nothing else than a rescaled tangential coordinates, up to a gauge phase. And this gauge phase is just the one which tells you that you can rewrite this AGL more or less like in this way here, like a purely tangential vector potential whose modulus is given by minus the distance from the boundary. what I want to underline in this slide is that you see that if ST are the epsilon rescaled boundary coordinates, then the main point to get the leading order is to be able to write psi GL as this product here up to a gauge phase. So you really separate the role played by the distance from the boundary and the tangential coordinates. And as you can imagine, this is not going to be possible in regions close to the corners, and this is actually our main difficulty in what follows. But these are just the three ideas you should have in mind if you want to reconstruct this leading order. And then what I want to say at the end is that if you then write psi GL in this way here, and you evaluate your Ginzburg-Landau functional just in the smooth part of the domain, then what you get is that this S coordinates just plays the role of making this quantity appearing, which is, if you look at the leading order, exactly what you want, at least in the smooth part of the domain, times this one-dimensional functional, which is actually the effective one-dimensional functional, which describes our energy. And in fact, this quantity E1D0 is nothing else than the infimum of this energy functional with respect to the real parameter alpha and the function f. So you see, this is how you can easily get the leading order. But if you want to go beyond, then you have to work a little bit more. And what you have to do is to look at the curvature of the boundary of your sample omega. So here I just denoted by K the curvature written with respect to the rescaled coordinates. And now again, if you have in mind that your psi GL can be written like this product here, and if you rewrite your Ginzburg-Landau functional using boundary coordinates, actually what you get is not what I showed you before, but it's, if you want to be precise, it's exactly this energy functional here. So you see that here, so before what I did was to put this quantity equal to 0. And in fact, if this is not here, this is not here, and this is not here, you just recover the energy function I showed you before. So if you want to go beyond, what you have to do is to take into account these contributions coming from the curvature. And if you do that, what you can say is that at least in the smooth part of the domain, you can describe your correction in this way here, where this E correction is just the energy functional here evaluated over the function F naught, which is the one which was realizing the minimum of this energy functional before. So actually here I'm going to be a little bit maybe too quick, because you could tell me that this functional depends on the curvature, and then it's natural to expect that that in place of this correction here, I should have something which does not depend on F0, but that depends on Fk. And this is true, but then you can do a some perturbation calculation, and you can show that at least to leading order, this contribution is still described by this F0. Okay, so what we want to do now is to look a little bit more about what happened, about how to describe the energy close to the corner. And here is the slide in which I would like to explain again to you why we defined the contribution coming from the corner in this way here. So first of all, in this picture, you see what is for me gamma j. So if you want here, I should write, if this is gamma j, this is alpha j. And you see that by capital L, we denoted this length here, and by the small l, we denoted this quantity here. So again, let me tell you that we want to minimize this quantity here in this domain here, which is just the domain given by all the psi in H1, such that psi in this part of the boundary satisfies some Dirichlet boundary condition, and these are given by exactly more or less the function I showed you before. So this is nothing else than the behaves you expect for psi GL close enough to the boundary. And in fact, what we say is that our psi GL should be more or less given by this quantity here, exactly here, so far enough from the singularity we have at the vertex. So then the main difference with respect to the smooth case is that here we are fixing the vector potential by F, and this you can do because what you should have in mind is that in our regime, the induced vector, the induced magnetic field, it's more or less equal to the external one. And if you have this in mind, then you can maybe see why this is a right choice for fixing the vector potential. And about this real boundary condition, then you see that if you calculate the energy here, you will have also contribution coming from not only this part of the boundary, but also from this part of the boundary. And what I wrote here is that we expect that not of all these, these boundary contributions do not affect the first order correction, just because this is very, very small, exponentially small here, according to our own estimates. And this is just a boundary we introduce ourselves to separate the region close to the corner and the one close to the smooth part of the domain. So again, let me say that here we take the limit as L and capital L are going to infinity, because you see now that we are sending these sides and these sides to infinity, because we are working in rescale coordinate, and then we are just zooming in close to the corner. And finally, what I want to underline is that the first part of the thing you should do if you want to study the first order collection is to prove actually that what you define as being the corner contribution is well defined. And in order to do that, in particular, what you should do is to prove that the fact that this limit exists. And let me just say that the existence of the limit is highly non-trivial. And this is non-trivial also in the case in which we are interested. So in the case in which if you want, these parameter L and capital L are diverging in the same order. And this is in fact the choice we will do at the end in our proof. And the main idea to prove the existence of the limits is to prove this through these three things. So the first one is monotonicity with respect to the parameter capital L. And then if you want, you should prove the fact that this contribution for any fixed L and capital L is uniformly bounded independently on these two parameters. And then what you should do is to be able to justify the fact that since you fixed your vector potential F, then what you want to do is to say that you can replace this F by a new vector potential. And here I wrote that this A it's more or less given by minus T times the tangential vector. This is true just far from the boundary, far from the corner. And the reason why, one of the reasons you should be able to say that this is possible is that if you just take into account this energy functional, then what you expect is that the leading order of this will be equal to this quantity here, in the case in which your vector potential is given by minus T times the tangential vector. And then if you want, this is necessary to cancel this diverging factor from the energy, from this infimum here. Okay, so after that, so now I presented just the two effective problems you should take into account in the smooth part of the domain and close to the corner. And then if you want to prove an upper bound and a lower bound for your energy, what you should do is to be able to replace your minimizing vector potential by this as I already told you, by this vector potential in the smooth part of the domain and by F in the region close to the corner. And then if you remember the corner region we defined, here we just neglected the curvature. And then what you should do is to prove that actually a rectification of the corner regions is possible. And then the last thing is to glue together the two effective problems, so the one in the smooth part and the one close to the corner. Here I didn't write any details, but let me say that this is also highly non-trivial because in order to glue together the two effective problems, then you will have some boundary terms appearing. And in fact, what we proved is that, again, if you look at this corner energy, then this is independent on the boundary condition you put in this domain here, meaning that this infimum is exactly equal to the infimum you will have in the case in which you take your psi in a different domain in which you put Neumann boundary conditions. And this is also an important part of the proof of our main result. So after that, what we want to do is to use our result to prove that actually superconductivity is surviving close to the boundary. And so what we should prove is an order parameter asymptotics. In particular, using our energy expansion, what we are able to say is that now if you look at the modulus of psi GL square, which remember denotes just the density of the Cooper pairs, then you can first have an estimate which is done in the L2 norm, and you can say that then the difference in the L2 norm of this of the modulus of your minimizing psi with respect to this f0 square, it's small in the limit epsilon goes to 0. And then if you use the refined energy asymptotic, what you can prove is that, so I didn't tell you, but to prove this, it is enough to know which is the leading order in your energy correction. And then as soon as you are able to extract the first order correction, what you are able to say is that it is true also this estimate in the L infinity norm. In particular, why this is really important. So first, let me say that this is just an estimate which is true in the smooth part of the boundary. And why this is really important with respect to the estimate in the L2 norm, because you see, if you just have this estimate, then you cannot exclude that close to the boundary, there are regions in which just a little bit of superconductivity is surviving. But what you want to prove is actually that close to the boundary, superconductivity is surviving in a strong sense. And this means that you should be able to say that this quantity here is strictly positive close to the boundary. And if you have such kind of estimate, then you can have what I just told you, because what I didn't say is that the quantity appearing here is strictly positive. So as soon as you have an estimate like that, you can say that this modulus is strictly positive at the boundary, and then you have you have uniform distribution of superconductivity. So unfortunately, since our corner energy is defined in such an implicit way, we are not able to extend this L infinity estimate to the full boundary d omega. But this is what we would like to have to prove that there is uniform distribution of superconductivity also close to the corner, which is actually what we expect. Okay, so now I try to convince you that if you want to improve the result, then what you should understand is how the energy close to the corner depends on the corner. And then this is why we elaborated this conjecture about to underline what we think is the right dependence of the energy close to the corner with respect to the opening angle beta. So before doing that, let me say that, so the main idea we had just looking at Gauss-Bonnet theorem, because if you remember in the smooth case, then the first order correction is given by something which is proportional to the integral of the curvature. And if you use Gauss-Bonnet theorem, then what you can prove is that this integral is actually equal to 2 pi. And then if you remember, this is the first order correction you have for smooth domain. And just by Gauss-Bonnet, you can say that this quantity is nothing else than minus 2 pi E correction. Since we expect that we have the same energy expansion, what we want to say is that what we did was, okay, let's look at the Gauss-Bonnet theorem in the case of a domain with finite number of corners. And actually what Gauss-Bonnet tells you is that if you look at this quantity here, then these two quantities are summing up to 2 pi. And then if you remember, our first leading order was given by this quantity here. And then since we hope and we would like to have the same correction we had for smooth domain, which is this quantity here, what you can say is to say, okay, let's start by here. Let's construct minus 2 pi. And then according to Gauss-Bonnet, what is still remaining is this quantity here. And then in order to have this equal to this, you see that you should put this quantity equal to 0. And this is actually why we conjecture that the contribution coming from the corner, which now I call beta, should be such that this quantity is equal to 0, meaning it should be equal to minus pi minus beta times E correction. Okay, so far this is just a conjecture, and I think that I have a few minutes to tell you what we were able to prove about this conjecture here. So this is the content of the third paper we wrote together with Michele, and what we studied, what we did was to try to prove that our conjecture was true, at least in the case of an almost flat angle, meaning that we look at an angle which has opening angle more or less like equal to pi plus or minus delta, where this delta is chosen to be very, very small. So now if you just look at the contribution coming from a corner whose opening angle is more or less equal to pi plus or minus delta, what you are able to prove is that then at least to leading order, this is given by plus or minus delta times a correction. And here I didn't write, but this corresponds in saying that we proved at least to leading order our correction because our conjecture, because our conjecture will be the following one, the one I just wrote. Unfortunately, we are just able to prove that this is the leading order. We still have some errors which are depending on delta and on the parameters we use to describe the region close to the corner. So here I just want to say that if you look at at what we proved for almost flat angles, then you see that there is a big difference with respect to what happened, what is expected close to the third critical field, because it is expected in that case that corners whose opening angle is bigger than pi just give constant contribution. Instead, according to our conjecture, what happens is that if you have a corner which is strictly bigger than pi, then these increase the energy. And if you have a corner with such that beta is smaller than pi, then these lower the energy. But there is no, according to our conjecture, there is no constant contribution to the energy coming from any angle which is bigger than pi. This is proportional to the opening angle. And as soon as you know that, as soon as you are able to prove this theorem here, then you can also write a corollary, meaning that now if you put together all the things I told you we proved, what we can say is that if you have a bounded simply connected domain in which just almost flat angles are appearing at the boundary, then you can extract exactly, at least at the first two reading or at the first two orders, what you expect is true in presence of corners. So exactly the same energy asymptotic you have for smooth domain. And in the last 3 minutes, what I would like to say is to show you which is the main idea of proving which is the explicit contribution coming from an almost flat angles, because I think that this is instructing also to underline what doesn't work for a general angle. So remember that this is the contribution coming from the corner in the way we defined. And then let me just say that, for example, if you want to prove a lower, so let's now look at just at what is inside this bracket here. So suppose that we want to prove a lower bound of this quantity here. What we can do is to introduce a trial state, which I denoted by psi trial. And what you can do is to do the following. So what you expect about this psi trial, you expect that this behaves as in the smooth domains far from the corner, so in the orange region in the picture. And then you have to glue together the trial states here and here just close to the corner. So what we did was exactly that. To suppose that in the orange region, the psi trial is given by this quantity here. Let me just say that this is nothing else than the gauge phase, which allows you to replace this f by the right vector potential. And then in the blue region, what we did was just to glue together these two trial states in the simplest way you can think of. So the phase now is nothing else than this phase here, which is the simplest one, which makes possible to have a continuous phase. So before concluding, I would like just to say that if now you calculate the energy of this trial state here, so I wrote here in orange the contribution coming from the region far from the corner, and in blue the contribution coming close to the bisector line here, which is actually, well, I didn't say, but I think it's clear. So this is exactly the point in which the tangential vector is having a jump. So this is the difficult part of the domain to work with. Anyway, from the orange region, we have this contribution. From the blue one, we have this contribution. And then you see that the role played by the psi trial in the blue region is just to cancel some contribution coming from the exterior part due to the fact that you are neglecting energy here. And then because of the jump you have along the bisector, in the blue region, you are able to reconstruct this quantity here, which is exactly the one such that if you sum this quantity times this quantity here, then you reconstruct minus delta times E correction. finally, in the lower bound, we did something which is really simpler with respect to the upper bound, because in this case, it is not a problem if you don't have a continuous space. In particular, it is enough to split in two parts your domain. And if you do that and you insert here and here exactly the trial state we used just far from the corner in the upper bound, what you're able to do is to say that you can prove a lower bound about this energy functional, which reconstructs exactly the same energy asymptotic we had for the upper bound. So in conclusion, what I want to underline is the following. So first of all, I told you that also prove the fact that the energy coming from the corner, it's well posed. It's not trivial at all. And I think that the main reason why at the end we are able to treat this quantity here is that in order to prove that this is well posed, then it is enough to work closely, far enough from the corner region, or maybe I should write far enough from the bisector line here, because this is the difficult part, or the part in which you have much more problem. And then I just show you which was the trial state we use in our analysis, at least for almost flat angle. And I told you that the phase we put close to the bisector line, it's actually the simplest one you can think about in order to have a continuous phase. But this is for sure not the optimal one. And I think that if one will be able to understand also in this simple case, which is the optimal phase, then this will be a really good starting point to prove the conjecture also for other angles. At the end, I also would like to sooner or later answer to this question about how we can characterize the distribution of Cooper phase close to the boundary. And I think that in order to do that, we should first understand better the contribution coming from the corner, meaning proving the conjecture. And something I would like to study also is what happens in the case in which number of corners is not finite, but this will be a really difficult problem. So for today, I stop here and I thank you for your attention.
Thanks, Emanuela, for the talk. Actually, before taking questions, I have one comment. It's about the first eigenvalue of the corner effective operator. Since Pavel is with us today, so he said that there are some rigorous results that it's an eigenvalue when the angle is less than pi/2. I think that Pavel just did improvement on this, and he arrived to some angles that are greater than.
We did some improvement, but I mean, we are still far from the optimal results.
Which is pi, yes, but you get up from pi/2.
So something which is up. Okay.
Okay, and well, I have one question also, and then it's about this when you build your model in this, which like. So you subtract from the Gunzburg-Landau energy there, the energy corresponding to the contribution of the smooth boundary.
Yeah.
And then
here, right?
Yes, exactly. So it's naturally to assume that what you will get there is this will reveal the contribution of the corners. But then actually you got something, I think it's in slide 12 or 9 maybe, slide 9. So you got, yes, here. So you got actually these terms in the next to leading order term E core times this integral involving the curvature, and these sounds. I was thinking, what if this contribution coming from the corners is just an illusion, and in this next leading order term, they just there's some hidden relation between E core and E corner that could cancel this E corner could
so, okay.
This conjecture, and I'm happy to know that I was thinking I think, right? At least for the flat, you said angles. But for flat angles, it's quite near to the smooth, so it's not the smooth.
Okay, so let me say that I hope that this corner contribution is not trivial for all the angles. And actually, one of the role played by the proof of the conjecture, let's say at least leading order for almost flat angles, is exactly this one, to exclude that at least for some angles this contribution is equal to 0, because we got first leading order which is not equal to 0. But you are right that so far we are just excluding that this contribution is not vanishing for angles which are close to pi. Yeah, I don't know. I trust our conjecture, so I think that the contribution should not be equal to 0. But you are right, we didn't prove this so far.
So we'll change the title of the talk then if there is no contribution. Yeah, and I don't know if it's fair to ask you if you just try to extend your results to study our case of a discontinuous magnetic field, since you saw this similarity between our case here near the intersection points. We can see this as two corners stick together. So maybe you think about something like that to extend your.
No, I didn't try so far, but what I think is that what could be true because of this analogy is that since your jump is along a smooth curve, then I think that could be simpler. First, look at your problem and then to go back to our corner problem, because my idea, if I show you the picture I brought you, is that in this case we really look at just what happened close to the corner, and we don't have to. So I think that this would be a nice idea to start first from your setting and then go back to our setting to understand something better.
Yeah, at least we cannot apply Gauss-Bonnet theorem there, since we won't be able to work on this closed curves. And also, I'm worried about what's happening in this edge, discontinuity edge zone. Anyway,
yeah, so this is the main problem. Yeah,
I was so excited, then I took time for everyone. Bernard, please.
Yes, just a question which is maybe simpler than what you have done. This is the question about the ground state for the Schrödinger magnetic operator with constant magnetic field in the sector. And so as was recalled, so there are results for alpha small by, for example, Virginie Bonailly. And then this was improved. So we have mentioned results by Pavel and collaborators. But in your approach, can you analyze the situation for just the angle close to pi? So we know that if it's more than pi, close to pi, we know that if it's more than pi, it's still theta naught, if I will remember. But so if we have pi minus delta, do you have the expansion for the ground state energy as a function of delta? It should be theta naught minus something. No?
Mm-hmm.
You don't meet this problem?
No, I didn't.
Because
no, but yeah,
it's a very natural question in the sense.
Yes.
Just to have the in this critical field attached to each angle, it's very natural to look at this perturbation. So
you're right. Thanks.
You don't look at. Okay.
No, thanks.
May I say something there?
Yes.
If I understand it correctly, Søren Fournet and Virginie Bonailly did look at this, and I think they have some result, but it's not published. But I think they have an eigenvalue below theta 0, just close to pi.
Okay, I don't.
As far as I understood, if I understood Søren correctly, but
Okay.
I haven't seen the result published.
Yeah, I have not also.
Yeah.
Okay. So this was just to mention the point.
Sorry, may I just interrupt? Okay, could you wait a second? Just want to add a comment. So I wanted to say exactly what Michaela pointed out, but also let me also say that the linear problem is quite different from the problem we are looking at. In our effective model is truly nonlinear, so you don't expect to be close in any way to the linear problem, even close to pi. So the two problems are really different. So well, there might be some connection, of course, but well, I don't know what it is.
Okay, thank you.
Okay, thank you, Horia.
So I have like a philosophical question also to Michele. I don't know, is it any chance to extend all this work to positive temperatures?
I don't know. This would be wonderful. Let me say that.
Well, okay. I think that the answer is it's really, well, it's a long answer actually, because you know, Gauss-Bonnet theory is correct close to the critical temperature. So if you get far from the critical temperature for the transition from say a normal conductor to a superconductor, if you stay close to the temperature, then Gauss-Bonnet theory is correct. You know it, you can prove it. If you get far from it, you don't expect it to be correct. Or rather, I mean, you just look at the many-body problem in a way. So
yeah, I mean, mathematically, I mean, do you expect the same type of?
Okay.
I mean, it should be more. It should be more regular. I mean, whatever you put there with temperature, I think it should be.
So you're thinking just adding some entropy to the functional and minimizing?
No, I mean not. I mean this C of yours. No, that's kind of.
Yes.
I mean not the ground state, but some sort of order parameter, something like that.
Mm-hmm.
And I mean, what if one could modify it in? I mean, I know that there are some physical models for temperatures which are way below the critical one.
Mm-hmm.
But that was only.
No, it's a good suggestion, but I don't know about the models, so you should just tell me what are the models. I'm curious about those models.
Okay. Do you have 2 hours or something?
Okay.
Okay, thank you. More questions? So, Ayman?
Yes, so my question is about the open problems. So what is, I don't understood exactly what you mean by the distribution of Cooper pairs. So.
Okay, yes, let me go back and then I write something there. You know, what I mean is that I would like to have information about the L2 norm of this quantity here, and in particular, what is done already for smooth domains is to prove an estimate not for this quantity, but at least for the L4 norm, because if you think about how so what you get from the energy expansion, then if you work a little bit, you can have an estimate for this quantity here. But the estimates so far we cannot improve because we have not enough information about what happened close to the corner. So I would like to first improve this. So to extend this estimate to the corner region, and then maybe to get the optimal one, which will be with the 2 here.
Mm-hmm.
But this, at least the one with P equal to 4, should be doable as soon as you have the energy expansion.
Okay, so you would like to extract the correction terms because for the leading terms we know
so
that.
Yeah, that's why this is that. I think that this is to be solved before than the third part.
Yeah. Okay. Thank you.
Welcome.
Thank you. I don't know, Pavel, if you wanted to ask because someone told me that maybe no. So it's a false alarm. Okay. Okay. So more questions? Let's see. I think no. So thank you so much, Emanuela, for this lovely talk.